Hello, my name is Emily Mixon, and I'm a PhD student at the University of Wisconsin-Madison. Today I'll be talking to you about optimizing argon geochronology analyses using an Isotopx NGX 600 mass spectrometer. Special thanks to my co-authors, as well as to the University of Wisconsin WiscAr Lab, Isotopx, Pycron Labs, and NSF GRFP program. So today I'm going to be talking to you about some of the special and exciting features of the newer NGX 600. I'll be going over the sensitivity of the proprietary ATONA amplifier and Faraday collector block. I'll be reviewing some work that we've done in our lab to identify optimal measurement and integration times for signals of various sizes, along with lengths and baselines. And I'll be discussing the gain and mass discrimination corrections for the ATONA Faraday configuration. I'll also end with some key takeaways and work that we hope to do in the future. To the side, you see an image of the NGX in the WiscAr lab that was installed in 2019. So some of the special and exciting features of the NGX 600. It's a multi-collector magnetic sector mass spectrometer. It, however, has a rotated exit pole piece that focuses the focal plane perpendicular to the ion travel path, and this helps improve collector efficiency and reduce volume. Most notably, it has a customizable collector block, which can consist of a combination of Faraday cups and ion counting electron multipliers. So shown in the figure to the side, the blue configuration is the all Faraday collector, with L5 being where we collect argon 36, and H3 where we collect argon 40. The configuration shown in red utilizes an IC cup for argon 36, and Faraday is for the rest of the isotopes. And it's been shown that the ATONA technology performs similarly to 10 to the 13 or 10 to the 14 ohm amplifiers, but with a significantly lower noise floor. So going forward in the rest of the slides that I'll be showing, we're using the all Faraday collection scheme, or the blue scheme shown here. One of the first pieces of work that we have done with the NGX 600 was quantify the sensitivity of the ATONA-backed Faraday configuration. So we did this using a variety of first principle standards for argon geochronology, which are shown here. We measured out masses between 200 and 1,000 micrograms of each standard material and fused them at 30% power for a duration of 60 seconds. And so we chose these standards in particular because they have independently confirmed isotope dilution data with which we can compare. This is a comparison of the sensitivity of the NGX alongside some of the other next generation multi-collector systems that are on the market today, are being used in labs around the world. And so you can see here that the differences in sensitivity are largely dependent on resolution, or the volume of the mass spectrometer, the resistor that's employed, and the trap current. It's important to note that the cathode source that is now standard on all NGX instruments can achieve a really high trap current of up to 1,000 microamps. This cathode source has not yet been installed in our lab due to COVID-19, but we expect that it will boost the sensitivity, hopefully 3 to 5-fold. One of the next steps that we took is to identify the optimal integration and durations for various signal sizes. So moving from left to right, we have 3 plots that show different signal sizes of argon 40 and argon 36 in an air shot. And so you can see here that longer integration times seem to be ideal for reducing our percent error on the 40-36 ratio. So as a result, longer measurement durations are also necessary, especially for small signal sizes. This is expected because it's been shown that noise on the ATONA scales inversely with time, which results in greater noise reduction at longer sampling times. And a quick note here, each point on these charts represents the average of 10 to 15 data points. So all in all, this is 2,300 air shots, which we've collected during COVID-19. We did a similar exercise for blanks. So again, the symbols are integration time, and the x-axis is our overall measurement duration. And we can see again that for blanks, longer integration times are also ideal. And as a result, though, we have a trade-off in that our overall measurement time also needs to be longer. We employ a similarly set up method for measuring baselines. So we measure baselines with 100-second integrations for generally greater than 800 seconds. And this achieves comparable data point density to measurements. As we can see here, the difference between 100 and 200 seconds on the integration kind of has a diminishing return the longer you measure. So we've chosen to utilize 100-second integrations for most of our data at this point. The next thing that we've developed for the ATONA-backed all Faraday collector system is a gain and mass discrimination correction. So mass bias is any mass-dependent bias that's introduced by variable either ionization or transmission. So we have 3 corrections that we make in the WiscAr lab. The first is the gain between the ATONAs, the second for inner Faraday bias between the collectors themselves, and the third being for fractionation that occurs at the ion source. So the ATONA amplifier gain factor is calculated using an internal routine from Isotopx. We do this about once a month or whenever we break vacuum. To test the inner Faraday bias, we measured both argon 40 and 36 in individual collectors in single collector mode, peak hopping with 50 cycles for each isotope in each collector. And so the data below indicate that there's actually negligible inter-Faraday gain. And we made these measurements over a period of a couple of months. And the MSWD value here, as well as the general sort of mean value, indicate that this is a pretty negligible contribution over the time scale at which we're making measurements in the lab. So that leaves us with the third correction. Since these first 2 corrections are both quantifiable and stable over the measurement period, we then must account for ion source fractionation. So in the all Faraday collection scheme, we can use atmospheric argon to assess the instrumental mass fractionation, and we've chosen to use an exponential law relationship to account for ion source fractionation. So assuming that we can either quantify the ATONA gain and that the inter-Faraday bias is negligible, this is the seminal correction that we're left with. So this is following after work that has been done with many different isotopic systems. So shown here in the numerator, the subscript A refers to the atmospheric composition. The subscript M is our measured ratio. And then these refer to the atomic masses of 40 and 36. So some of the key takeaways from the work that we've done so far. Sensitivity on the cathode source is expected to improve with the installation of the new source. But at present, advantages of the NGX-600 include that it has a high resolution, a large dynamic range, and that we can use this all Faraday collection configuration and not have to worry about peak hopping or calibrating between different collector types. We've found that it's important to optimize measurement conditions for signals of various sizes and carefully characterize our blanks and baselines. We believe this is fundamentally important to making best practice measurements of geologic materials. And then gain bias corrections are also important for the future of our community, and we find them to be more straightforward with measurements on a single collector type, like the ATONA-backed all Faraday configuration that we've used here. Some next steps that we're going to take include defining a threshold for argon 36 that can be accurately measured on the ATONA-backed Faraday. So we do have the option to measure this isotope on an ion counter, and we want to know what the threshold might be for doing that, and also figure out a calibration in case we have to utilize it. We are going to be measuring a range of previously characterized geologic samples, including both single crystal fusions and ground mass, ranging from Permian to Pleistocene in age. This endeavor has been a little bit delayed due to COVID-19. And once it is installed, we're also going to be comparing our current prototype source with the Isotopx new Nier-type gas source that allows for variable trap current setting. So this is the source that is coming installed in all NGXs that are getting delivered today, and we're excited to compare it to the work that we've done here. So thank you so much for watching the talk. I'm happy to chat in the live session as well as take questions during that time or via email. Special thanks again to my co-authors, as well as to the NSF for my personal funding, the WiscAr Lab, Isotopx, and to Jake Ross at Pycron Labs for his computer support.